right, as we get started, go and turn your textbooks to page 97, and want to look at an application of graphing linear equations. You'll recall way back in chapter 1, this goes back to probably September, we discussed taking a statement or a rule in words and translating it into an algebraic formula or equation. For instance, you look at problem 21 there on page 97. Go ahead and read the problem for us there, if you would. Number 21. Bracken?
The perimeter P of an equilateral triangle equals 3 times the length of the side X.
Now that's a rule stated in words. How could I translate that into a formula? Maddie? Good. P equals 3s. We remember doing things like this. Well, if you can translate a formula, a rule into a formula, particularly a formula that has only 2 variables, one independent variable and one dependent variable, and both of them are to the first power, then you could graph this as a linear equation. But you wouldn't have x and y axes. Instead, we would let the dependent variable take the vertical axis and the independent variable take the horizontal axis. So just throwing a quick sketch up here, instead of x and y, my horizontal axis would be the s axis. My vertical axis would be the p axis. You see that? And of course from here we could label all these fun things and all that stuff. Okay, and then of course we could set up not an XY table, but an S instead of X, P instead of Y table. And we could pick random values to plug in for S. For instance, class 0, 1, and 2. And we could plug those in, and we could say, well, if S is 0, then the perimeter is 0. If the sides are each 1, then the perimeter is 3. If the sides are 2, then the perimeter is 6. And we could plot those points, 0, 0, over 1, up 3, over 2, and up 6. And we could connect these points with a straight line. Now, here's where this breaks down just a little bit. You're representing perimeter and sides. Can you have negative lengths of sides or perimeters, negatives? No. So really then in that case, we don't need the negative ends of the axes. We could simply start it at 0 in that case. Does that make sense? Questions though, do we see it's really the same thing as what we were doing, just replacing, instead of x, the independent variable, and instead of y, the dependent variable. What I'd like you to do, we're going to graph them in just a moment, but I want you to do on numbers 22 through 26 is to translate each of those rules into a formula. So just a few minutes to do that. We'll go over those, make sure they're correct, and then we'll graph just a few of them. Doing numbers 22 through 26. Everybody's got them. Good, Noah. Good, Reckon. All right, let's go and take a look at these together. Number 22, it says the cost C of producing X units is $2,000 plus $1 per unit. How many of you watch Shark Tank? Okay, so a couple of you. It's basically a show. It doesn't have anything to do with real sharks, by the way. But you've heard of a loan shark? Okay, somebody who loans out money with the intent of making money back, right? Well, anyway, there's groups of several investors, really rich people who've been wildly successful. They've started their own business, they've made a ton of money, and they want to make more money while they help other people do the same kind of thing. And so you'll hear people come onto the show and they've got this great, cool idea for a new product. They just need help getting it off the ground. And the sharks, these investors, decide whether or not they want to invest in this other company or not. And a lot of times they'll ask the person, okay, how much does it cost you to make this item, for instance? Well, if it's a smaller item, they may say, it only costs us $1 a unit to make it. They say, how much do you sell it for? $9.95. I like the margins. You know? Well, it may cost them $9.95. It may only cost them $1 to make it after they pay for the equipment to make it, right? That's the $2,000 here. Up front, $2,000 worth of equipment to manufacture the item, and then it's $1 per unit to make. Does that make sense? How would I write that as a formula, though, Gavin?
C equals, well, it's probably wrong, but I put X times the quantity 2,000 plus 1.
Yeah, that's not correct. Thinking more logically about it. They pay $2,000 up front for the equipment, and then, in addition to that, they pay $1 per unit. Noah, help him.
I put 2,000 plus 1.00x.
Good, and we don't even technically need the 0.00 because I'm lazy. In fact, we technically don't even need the 1, but 2,000 plus 1x, right? Now here, x would remain the x-axis. The y-axis would become the c-axis, right, if we were to graph. Taking a look at number 23, the number of yards, y, is equal to the number of feet, f, divided by 3. Back to Gavin for redemption.
Y equals f divided by 3.
Good, and hopefully use a fraction bar to show that division, right? Y equals f over 3. Number 24, Maddie. The gross profit, GP, of an item equals the selling price, P, minus the $2 cost of producing the item. Louder. Good. GP equals P minus 2. How about number 25? Brecken. The number of tablespoons, T, is equal to the number of teaspoons, X, divided by 3.
T equals X.
And for our last one, number 26, the wages, W, for assembling toys in a factory equals 2 times the number of toys made, N. Gavin?
W equals 2.
And W equals 2N. Now, if we were to take the time to graph here, right, if we were to do that, understand a number like 2,000 is going to make for some difficult graphing, right? And me being lazy, we're not going to bother with that one. But I am interested in maybe doing these 3 graphs here. Do we see that this one, the teaspoon or tablespoon teaspoon problem, is going to be the exact same looking graph as the yards and feet problem? Okay. Now, here would be x-axis. Here it's an f-axis. Here it's a t-axis. Here it's an actual y-axis. But as far as the graphs are concerned, this is approximately what they would look like. If you would go and get out some graph paper. And can we have negative feet or negative yards, class? No. So let's set up just a small first quadrant. Just set up a small first quadrant. And if we're going to graph y, yards, equals f feet divided by 3, the vertical axis, class, is going to be which one's the vertical axis here?
Oh,
No.
wait, no, why?
Y. Y, capital Y in this case. But yeah, the y-axis is going to be my vertical axis. And the horizontal axis will be the f-axis. All right? And, of course, the 0 of both number lines is this bottom corner. And then from there, 3, 6, 9, and so forth. Then 3, 6, 9, and so forth. All right? And we need to set up not an x, y table, class, but an f, y table. And we're going to plug in values for the f because it's not by itself. And we want to pick strategically. 0, 1, and 2 might not be my best numbers here because I'm going to have to divide the f by a 3. So what's a good first number? 6, okay. 3. 9 could work. I like 0. But anyway, so 6, 3, 9 would work, okay. And now notice my f-axis, that's about all the room I've got, okay. If I were to plug in a 6, then class I get out a 2. Plug in a 3, get out a
1.
Plug in a 9, get out a 3. So we're going to plot those 3 points on your graph here. We've got a 0.62, we've got a 0.31, and then the 0.93. Remember, you're going over and then up. And using your straight edge, simply connect the dots. Now, you know 0 would have produced a 0, so it should hit the origin, and in fact it does. And here we see the linear equation graphing the relationship, a picture of the relationship between feet and yards. Questions on this graph? I had to set up another one. Let's go and set up another graph here. And for gross profit, could gross profit ever be negative? Technically, it would be considered a loss at that point, right? But if we're saying our gross profit is selling price minus 2, well, unless we sold something for 0, it's really not going to go far into the negative. So for practical purposes, once again, let's just set up a first quadrant graph. Technically, there's a little room for negative here, but we'll just stay in the first quadrant, I think. But we're not going to have x and y axes here. Instead, my horizontal axis, class, is going to be the P axis. That's the selling price. And the vertical axis is going to be the GP, gross profit axis. Of course, 0's still the origin. And since I'm avoiding negatives, when I set up my PGP table, I need to make sure I don't start with 0, because that would produce negatives, and we didn't really allot room for negatives on our graph. So the smallest number I can plug in for P would be 2. Another number we might plug in? 4. Another number? 6. Okay? Now, we're not dividing by 2, so we don't have to use even numbers here. We could have done something like 11 or something random, but it's perfectly fine to go with this. And as far as the GP values, well, if you plug in a 2, you get, you plug in a 4, you get, and you plug in a 6, you get 4. Go ahead and plot those points. 2, 0, 4, 2, and 6, 4. And this shows exactly what you would think it would be. In order to break even on something, no profit at all, you have to start at $2, and you see that. The graph must begin at $2 sell price. Anything beyond that just brings in more profit. So here's the thought, I mean, theoretically, the more we charge for the item, the more profit we make, right? That's not entirely true. When would that not be true? Like, why not just charge $5,000 for it? Gonna make a whole lot of profit.
If you charge too much, people are not going to buy
If
it.
you charge too much, people aren't gonna buy it. Yeah. For instance, you all remember, this is charging for services, right? But like in the NFL, a player wants a certain amount of money. Now he's got to be careful because he wants to get as much money as he can make because he's greedy, right? Like all of us, deep in our heart of hearts. But if he asks too much money and nobody's willing to give it to him, he doesn't get anything, right? Yeah, and that's the problem with some people, right? They just want too much. And you know, who was it? There was Cam Newton, I think, ended up taking $1 million, which, again, just $1 million sounds like a bunch. Okay, to an NFL quarterback, that is nothing. He's basically playing for free. You know, again, we can't fathom that because we don't deal in millions of dollars. At least, I don't think any of us do. If you do, talk to me after class. But anyway, he was willing to, he said, look, I want to play. I want somewhere I can go to play. So we went to the Patriots, played for $1 million, didn't do great, probably won't get another contract. But, you know, the point was he made some money. Any money's better than no money, right? So, yeah, technically what you look at, hey, let's charge $11. Then we make a profit of $9 on this item. If somebody's willing to pay $11 for your item, right? That's the law of supply and demand. We'll talk about that more in economics class. Let's take a look at our last one here. The wages for assembling toys equals 2 times the number of toys made. You all might remember the term piecework wages from your junior high days. And so a person on an assembly line might be paid a certain amount for every item that they complete on the assembly line. My great-grandma worked in an automobile factory way back in the day, like Henry Ford type days, okay, assembly line. And her job was to put the button on the steering wheel for the horn. So all day long, car would come down the assembly line, she put the button on. Next car comes, button on. Next car comes, and for every button she got on, the more she got paid, right? So work fast. Piecework wages. That's kind of what we got here, except we're making toys, and we get $2 for every toy we get made that day. So you want to make a lot of toys, so you make a lot of money, so you can eat, because eating's good, right? Y'all agree eating's good? All right, let's go ahead and set up this graph. Now again, you can't make a negative number of toys, right? How many toys did you make today? -3. I saw 3 on the line and I destroyed them all. Okay, probably unrealistic. So let's not set up any negative space on our graph. I can get morbid really quick, so we'll stay off of that. I know Brecken's tendencies. I have heard of things. Anyway, remember the camera. Remember the camera. All right, and our axes, again, they're not going to be X and Y axes. They're going to be N for the horizontal, W for the vertical. You can't get away with nothing at this school. Yeah, I know. Rough life, isn't it? Just remember, God is also always watching.
Watching you bully me.
What?
Watching you bully me.
Oh, hardly bullying, my man, hardly bullying. All right, all right, so we need to set up, again, not an XY table class, but an NW table. And let's pick some random numbers to plug in for N. 0.
1 and 2.
1 and 2. Hey, why not? All right, so if I plug in a 0, I get. Plug in a 1, I get. 2, plug in a 2, I get. 4. Let's go ahead and draw the graph here. Of course, 0, 0, you make no toys, you get no money. You make 1 toy, get $2. Make 2 toys, get $4. And again, simply making a picture of the situation here. So obviously you can see more toys, more money. Questions on graphing formulas. Understanding oftentimes with formulas we may not have a negative region to the graph, or negative regions, maybe only a first quadrant. Now, an obvious exception, if you look across the page, you see the formula for the Celsius and Fahrenheit conversion. Now, here's a space where, although they only mainly used the first quadrant, should they have allowed for other quadrants? Yeah, because can you have negative temperatures? All except on the Kelvin scale. Y'all learned Kelvin scale yet? Yeah, no negatives there, right? But none of these was Kelvin. So yes, we do need negative areas here. They kind of showed a little bit of it, but certainly the graph would just keep going and going down into those negative areas. Questions on formulas? All right. Let me let you work some classwork then, practicing just graphing ordinary XY equations again. So go ahead and set up a true full Cartesian plane now on your paper. And if you can do 4 different things, maybe pencil solid line, pencil dotted line, pen solid line, pen dotted line, you could do all 4 of these graphs on the same grid. If you have more colors, of course, that works as well. But I want you to do page 100, 9 through 15, the odd. Page 100, 9 through 15, the odd. Like yesterday, I'm going to give you a head start. And then I'm going to start graphing so that as you finish, or as I finish a graph, you can check and see if your graph is correct. Make sure you get in the habit of putting arrowheads at the ends of the axes. Make sure you get your X and Y labels on there. So that on the quizzes and tests, you're not going to be as likely to forget things like that. Certainly would hate to lose cheap points that way.
Good. So far looks good. Alright, okay, you went ahead and analyzed all of them.
Alright, for sake of time, go and stop where you're at. Check your number 9. You should have had an equation kind of on the outside of all the other action that kind of went through the tens on your axes if you made them that far. Did we get that white line equation correct? Alright, for the next one, the number 11, again here you could have moved either x or y over, didn't matter. Here, move the 2x, leave the y as is, move the 2x as a negative, and again, plugging in for the x now, and your yellow line equation should have come right in here close to the y-axis. Not vertical, but not real slanty, almost a vertical drop. Do we get a line like that for the second one, number 11? All right, for the third one, here the 2y is the obvious choice to move, so the x stays by itself, now plugging in for the y. And this equation would have kind of slanted a lot more gradually out toward this white equation. I wasn't able to quite hit it, but you can see it almost would have hit if we'd gone a little further with my graph. but should have gone through the 4 here, just like the yellow one did, and it would have hit out here at the 8 as well. Did we get that graph for the third one? Did not. All right, let's take a look at that real quick. Is that the dotted line that you have there? All right, 8 minus 2y. So you've moved the 2y over as a negative correctly. Okay. You see how you did a yx table instead of an xy table? Yeah. So we've got to make sure we put the x is 4, then the y is 2. The x is 2, and the y is 3. This is why when I told you how to set it up, I said make sure we set it up x then y. For that reason, so we can literally just plot the points exactly as they are. So you got away with it on the others somehow. Oh, you wrote yx, but you treated it like xy. That's the only reason you got away with it here. Here you could have gotten away with it regardless because of the way it happened to work. And then here it burned you. So yeah, x then y, very important. But everyone else, I think we said yes, we're good to go. Now this next one was weird because there really isn't a good choice of letter to get by itself, right? Neither one already is just a plain old x or a plain old y where, well, just ditch the 2y or ditch the 2x. Well, if I ditch the 2x, it's a 3y. I have to divide by a 3. Or if it's a ditch the 3y, which is what I did, then you have to divide by a 2, and that's a pain. Especially because when we come over here, we get this big ugly fraction. I'm like, well, what do I plug in for y? Well, normally I do 0, 1, and 2, right? When you plug in a 0, that's 12 minus 0 is 12, divided by 2 comes out easily to 6, right? But if you try to do a 1, 3 times 1 is 3. 12 minus 3 is 9. 9 divided by 2 doesn't come out evenly. Now, I suppose we could do a 1 for the y and a 4.5 for the x, right? Go over 4.5 and up 1. Okay, that point could work, I guess, but you're gambling that you can plot a half really accurately, right? Then the 2, well, that actually works out okay because 3 times 2 is 6, 12 minus 6 is 6, which does divide by 2 to get 3. So kind of realize we want even numbers here, right? Since there's a divisor 2, using even numbers ends up working out pretty well. But that's just a bit of a pain, isn't it? When neither letter is all by itself to begin with, do you see that a table method can be a bit of a frustration? Which brings us then to our second method of graphing linear equations. Method number 2, Roman numeral 2, under graphing linear equations in your notes, is using something we call the intercept method. Roman numeral 2, under graphing linear equations, is what I call the intercept method. Now, first of all, since I'm a football guy, so here we go. An interception is when the defender, the defensive back, cuts off the quarterback's pass, correct? Now, technically, he doesn't just cut it off, like he actually grabs it, not just knocks it down. Okay? Pass breakup and intercept. But interception is when it cuts off. Well, you realize when you draw a line has to cut at least one of the axes, usually both of them. Like a straight up and down line would cut the x-axis, but it would run parallel to the y-axis, right? Or a horizontal line would cut the y-axis, but be parallel to the x-axis. But most lines are going to cut the y-axis somewhere and the x-axis somewhere. These points are called intercepts. This point would be the x-intercept of the yellow line. This point would be the y-intercept of the yellow, the pink, and the purple lines, okay? They all happen to cross at the same y-intercept. Go ahead and jot that term down first of all. The intercept is where a graph crosses an axis or cuts off at the axis. It's cut off at the axis. But an intercept, not intersect, an intercept is where a line intersects the axis, but the term is intercept. Okay? It is an intercept, that is a thing, and the action that it does is it intersects the line. Okay? So the x and y intercepts are points where the graph, the straight line, the linear equation, will cross the axes. Here's the deal. Where you have an x-intercept, for this point, let's go with the purple line actually. Well, the x-intercept is that point 6, 0. And in fact, anytime the y value is 0, the line would have to cross the x-axis, right? Because for every point on the x-axis, the y value is 0, correct? So what we're going to want to do with the intercept method is simply find the intercepts. So first of all, find the x-intercept, which is something 0, by plugging in 0 for y. Find the x-intercept, which is something 0, by plugging in 0 for y. We're going to use this same equation to show how this could have been done much quicker with the intercept method. First of all, I don't have to rearrange a thing. I can leave the equation exactly as it is. And I say, okay, I want to know the x-intercept. I'm going to plug a 0 in for y. So I come right here, and I put a 0 right there. Well, when you put a 0, what happens to the entire term then, class? The whole thing just becomes 0, and basically then drops out. It's worthless. So basically, I just get 2x equals 12. Well, what's x? 6. Well, that was pretty easy, right? Well, that's only one intercept. We now want to find the other intercept. So number 2, find the y-intercept, which is 0 something, by plugging in 0 for x. You probably saw this coming. So I got the x-intercept, I plugged in 0 for y. Now I need to get the y-intercept by plugging in a 0 for the x. So going back to what we originally had, 2x plus 3y equals 12. Now I plug the 0 in for the x. Well, what happens to the whole term with the x? Gone. I got 3y equals 12. What's y? 4. Now, normally I told you we want 3 points for a straight line, right? What are the odds I screw up a 0? I wouldn't have made it to 9th grade if I screwed up zeros, okay? Covering up a term and just knocking the whole term out, you can't possibly mess that up. Most of you. I don't know why I'm looking at Noah. All right, so Bracken's like, yes! Anyway, so I'm going to gamble that with zeros, I ain't screwing it up, and I'm only going to go with those 2 points then. So, next step, plot the intercepts and connect the dots. Plot the intercepts and connect the dots. So under this method, I find 6, 0, I plot it. I find 0, 4, I plot it, and I connect the dots, and I'm done. Super quick and easy, especially when you can't really get a letter by itself easily. Now, take this example if you would. 5x plus y equals 10. For sake of time, we're not going to actually graph it. I just want to practice finding the intercepts. Now here, I could get the y by itself pretty easily, couldn't I? But I could also find the intercepts pretty easily. I first of all want to find my x-intercept. It's important to remember that every point on the x-axis has a y value of 0. There's a literally infinite number of x values, but the y value for all of them is 0. So I'm going to plug in 0 for y. Essentially, I cover up the y. That's plugging in the 0. And I get 2. Then I'm going to find the y-intercept. Well, again, it's important to remember that everywhere on the y-axis, we have an x value of 0. So I just plug a 0 in for the x. What do I get for y? 10. So I'm going to plot at 2, 0, my x-intercept. I'm going to plot at 0, 10, my y-intercept. And we draw that line and I'm done. Seem easier than the table method, right? And here we could use it even if the table method could have worked, but this is faster, and I'm lazy. I like zeros. They're very easy to plug in. Other numbers aren't as easy. I like easy. Write this equation down on your paper now. Negative 4x, positive 6y equals 12. Negative 4x, positive 6y equals 12. We want to find the x-intercept and the y-intercept. How do I find the x-intercept? Gavin?
Do it by plugging in a 0 for y.
I want the x-intercept, so I want to plug a 0 in for
Y.
the y. In other words, the other letter. Okay, so if it's an x-intercept, that means the y is what needs to be 0. And when I plug a 0 in for y, what do I get for x, Gavin? How do I get the x by itself, Gavin? Help him, Noah.
You divide or multiply. Wait, divide.
Divide away the,
4.
it's not a 4, the negative 4, right? Divide away the negative 4 from both sides. I mean, if we were working an equation, and at the end of the equation we got this, you would say, oh, divide both sides by negative 4, right? Well, that's why visually you're cutting off the y. It's gone now because there's a 0 plugged in for it. And we get what for our x value, class? Negative 3. For redemption, Gavin, I want the y-intercept. That means I need to plug in
0 for x.
0 for x. Gavin, if I plug in a 0 for the x, the whole term drops out. What do I get for y? 2. Draw a quick, just on your paper, just a real quick little sketch like this. And mark off a couple values there, mark off a couple values here, and here, and here. And I'm going to plot my x-intercept, class, at -3, 0. My y-intercept at 0, 2. And then we simply connect the dots. That's kind of a quick sketch of what it would look like, just for sake of time, as opposed to doing a whole graph right there. But you see how quick and easy this method can be. Let's take a look at another one. Sometimes they don't work out quite as neatly, but they still work out, I would say, fairly easily, though there is one more method coming that will make this even better. 7x is equal to 15 plus 3y. 7x is equal to 15 plus 3y. I don't want to have to do the table method, because there's not a letter that's easy to get by itself. So if you don't want to do the table method, class, you can do the intercept method. There we go, the thing that's on the board that we just talked about. And for the intercept method, the key is to plug in a couple of zeros. When I'm finding the x-intercept, class, the 0 goes in for the y. Now this isn't going to be pretty. Plug a 0 in for the y. What does the equation look like now, class? 7x equals 15. So what's x? Ooh. Divide both sides by 7. You're getting the x by itself. Careful, dividing both sides by 7 to get 15 sevenths? What in the world is 15 sevenths? Well, you're going to have to go mixed number here, aren't you? In order to know where to put the point. Where is it, class? 2 and 1/7. In other words, just a seventh of something is so small, right? So just a tiny bit above your 2, or to the right of your 2, right? Just a little beyond 2. All right, then we need our y-intercept. All right, for the y-intercept, we have to plug in a
0
for x. Be careful here. When I plug a 0 for x, the equation becomes 0 equals 15 plus 3y. What am I going to have to do? Move the 15 over as a negative 15 equals 3y, so that y is going to equal negative 5 when we divide away the 3. But still, I would contend this is easier than dividing both sides by 7 to get x by itself and setting up a table and trying to figure out all those values to plug in. That would be my contention. And so again, if we were to graph this, we would say just a little beyond 2, right? So here's 1, here's 2, here's 3. 2 and 1/7 would be something like this, right? And then 0, negative 5 would be down at negative 5, and then we would connect those dots there with our graph. Any questions on that one? One more together and then we'll be done. Even if there's a fraction, this method's not too bad. 1/2 x positive 4y is equal to negative 8. a half x plus 4y equals negative 8. At your seats, find the x-intercept. All right, hopefully you plugged in 0 for y. And when you plugged in 0 for y, it should have left you with a half x equals negative 8, right? What do I do to get the x by itself? Divide 1/2. But do we ever, stay with me, divide by fractions? We multiply by the reciprocal. We should actually multiply both sides by 2 to get negative 16 for my x-intercept. Then for the y-intercept, at your seats, find me the y-intercept. Much easier this time, isn't it? Hopefully you plugged the 0 in for the x and easily got y equals negative 2. Now the graph of this is going to be just a little rough because your x-intercept is way back here at negative 16. So you go back 16 lines, you didn't even count, but something along these lines, and then down 2, and you get a line that looks something like that. Okay? Questions on this? We'll practice more with this in our next lesson. There is no homework this evening. Have a wonderful rest of your day. You are dismissed.